All right, good morning, everybody. Today is the 18th of October, and we are beginning our path through Chapter 5 and Chapter 6. Chapter 5, we're going to cover sections 5.1 through 5.3, and the topic of Chapter 5 are shear moment diagrams. Section 6.1, 3, and 4 will be covered in Chapter 6. So the topic of that are shearing stress distributions, and this will prepare us for a take-home quiz over chapters 5 and 6 sometime around November 8th. So here is the first question I wish to ask of you. If you design a structure, this is very general, this is not a mathematical question. What do you not want it to do? Say it again, yes? Fail. Yes. You do not want it to fail. And that is correct. So if you don't want it to fail, since, as I've said before, failure is an option, it's just a very terrible option, but since you don't want it to fail, what part of the structure do you design for? Or what part of the structure do you design for? In other words, do you design for the strongest part of the structure, the average part of the structure, the weakest part of the structure? Yes, you design for the weakest, because once the weakest part fails, it fails and it's no longer a structure. So, along with that same idea, designing for the weakest part of the structure, what load do you design for if the load is distributed? So in other words, if the load is different from one end of the beam to the other, do you design for the smallest load, the average load, or the largest load? Yes. You want to design for the largest load. So you want to design for the weakest part of the structure, the largest load, and then you include a factor of safety so that once you've thought of everything you can possibly think of and designed for the weakest link in the chain and the strongest pull on the weakest link in the chain, then you still want to gin it up because you want to make sure that it doesn't fail if there's a snowstorm and, you know, army troops marching on your roof and nuclear attacks and so forth. So you want it to last to the point of almost, I wouldn't say ridiculousness, but you want to be very, very certain. And this is really the desire to not have structures fail at inopportune times. I mean, we design things for failure. For example, I was sitting in on Ray Floyd's ES1000 class yesterday, and he's talking to his class about putting together a marketing plan for a particular kind of a toaster. Well, the toaster costs like $12. So you don't design to repair the toaster. You design to throw the toaster away. If the toaster goes bad, if the heating element dies, if something happens to it, there's no economic incentive to storing parts in different warehouses. What you want to do is just have that, you want to keep the cost low enough so that the toaster can be thrown away. In the same way, we generally design roads. If you're designing a highway, you generally design a road for about a 10-year or a 15-year life. It's spec'd out by the Department of Transportation. But if you think about it, why do you suppose we don't design? What is one reason that we don't design a highway to last forever? Cars? Cost, absolutely. Absolutely cost. Also, what happens to traffic patterns? Like, yeah.
In Yellowstone, where I was working, it needs to be way wider than it is.
Very true. Yes, because when the roads were put in with horses and buggies way back in the day, nobody anticipated that there would be thousands and thousands and thousands of tourists every day in the month of May, and now there's just not enough road for that. So we take into account the idea that we need to have an opportunity at some point in the future to do something different to that road, and we don't really even know what it is. I mean, right now we think about traffic pressure or changes in routes, you know. But so you don't design everything to last forever, but you want it to last the way that you want it to last, whatever that happens to be. We also tend to design bridges, for example, to last longer than roadways because they're just more expensive and they take more planning. So you sort of over-design a bridge in a way that you don't over-design a road. So it's all part of the design process. But in general, what we want to do is to identify where the largest load is going to be and where the weakest link is going to be. So the subject of Chapter 5 is, if we have a distributed load, so in other words, the load varies from one side of the structure to the other, where is the load the greatest? And since we're in mechanics of materials, we're really talking about the internal response to that load. So in other words, we're talking about shear and moment. Now, if you think about it, shear is the force that results, let's say that causes a shearing stress. So in other words, when we say shear, we're talking about some load which we're going to start referring to as V. And a shear is a force that causes a shearing stress, tau, which then would be some V over A. All right? And a moment, we know, is not a force, but it's a moment, but it causes a normal stress like this. Sigma is equal to MC, sigma max is equal to MC over I, or sigma is equal to My over I. And of course, we have a negative to indicate that a positive moment will result in a negative sigma toward the top of the beam. Now, one of the things that we have not talked about, we know that a moment that looks like this is positive. And we have not really talked about what kind of a shear is positive. It's a little bit trickier because if you think about it, if you have a beam and you cut it in the middle and there's some shear, if the shear looks like this on the left, I mean, in other words, if I've cut it on the right side and the structural member is to the left, it's going to look like this on the right. Because they still have to be equal and opposite, and if they're not equal and opposite, then something's going to move or break. But we use this as being a positive shear and this as being a positive shear, meaning that if we have a structural member and we cut it, we start at the left and we cut it on the right, downward on a right face cut is positive. But if we start on the right and move to the left, and here we have a cut on the left, that up is, positive, right? So our sign convention for shear that we'll be using for the internal load is this is a positive shear, this is a negative shear, this is a positive shear, and this is a negative shear. Okay. Now, that's the sign convention that's more typical. It's not 100% true, but it's a sign convention that your authors use pretty rigorously. So I'm going to stick with this so that you can refer back to your textbook if you are questioning the sign of your shear. All right. Now, since we are ultimately looking for tau max and sigma max. There are two parts to this. This is going to be V over A. This is going to be P over A, or My over I. We have a couple of different ways that we can maximize tau, for example. Tau can be maximized if V increases or if A decreases. Sigma can be maximized if the moment increases or if the moment of inertia decreases, or if P increases or if A decreases. So what we're talking about today is just one component of this setup. We want to know the magnitude of V across a beam, and we want to know the magnitude of M across a beam. So the other thing to think about here, I don't even know if I want to say that. We have a different meaning when we have positive sigma max, or positive sigma or negative sigma. Positive sigma means tension, negative sigma means compression. And they are two different physical phenomena, aren't they? Well, if tau is negative or tau is positive, it's the same physical phenomena. It's just a difference in direction. It's important to keep it straight because sometimes you have to add or subtract magnitudes, so you always want to do it the same way, or at least you want to know which way you're considering positive and negative, which is why we develop a sign convention. All I'm saying is it doesn't have that same physical meaning as sigma, negative meaning compression, and tau, and sigma positive meaning tension. It just means it's a difference in direction. You still have to keep it straight, but it is a little bit, there's a little bit less physical meaning to it than positive sigma or negative sigma. All right, so if we talk about the types of structures that we're going to look at in this chapter are basically beams that are supported in different ways and then loaded in different ways. But a beam that's like this, where you have a fixed support and a rolling support, is just referred to as a simply supported beam. Okay, another way that we can support a beam is in a more continuous fashion, where you have more than two supports, and the way I have it, this should be a rolling support when it goes like that. So that's referred to as a continuous supported beam. We have another type of beam which is called an overhang beam, where we have simple supports, one rolling support, but that one end is not supported. We also have a beam that can be fixed at one end and supported at another. Like this. Then we have a beam that's extruded from a wall. This is referred to as a cantilever beam. Or we have a beam that is rigidly fixed into two walls, and that's just called a fixed beam. Now, the reason that we have them this way is that these are statically determinate. In other words, you can figure out what the reactions are using methods of statics. These are statically indeterminate, meaning you're going to have to use a different method, such as we're going to have to use something similar to the method of joints or sections. Basically, we're going to have to use some method of deflection to determine the reactions in these types of beams. So we really like the statically determinate beams. And we're going to start our discussion today with a simply supported beam. And we'll look at different ways that we can load that beam. Okay? If you have a simply supported beam, the type of loading that we've talked about so far would be point loads. So for example, you have a beam, this is going to have some reaction, this is going to have some reaction, and you have some load on it, P. You can do statics to determine how much of that P is supported here and how much is supported here. Now something that we haven't talked about, oh, you can have several of those. You can have a P and a P1 and P2 and so forth. So you can have several point loads. Now, the other type of beam that we're going to talk about this today, and we're going to talk about one other type of loading condition on a simply supported beam, which is a distributed load, where you might have something that over some span of the beam, you have some sort of a W, which is in a load per foot. Okay. Now, one example of a distributed load, back in the old days, this is the way they modeled traffic on a beam. Because if you think about it, you could model traffic on a bridge, for example, as being a bunch of point loads. But really, at different times, you can consider traffic to be a distributed load that is so much weight per foot. So at times when there's heavy traffic pressure, the weight per foot value goes up. Instead of, if you were to analyze it this way, you would just have to put in a whole bunch more point loads. So if the traffic is evenly spaced, which just generally is until you have a wreck, you can model it with a distributed load. There are other types of distributed loads as well, but that's just one as an example. All right, so we're going to start with a simply supported beam and a couple of point loads, or maybe even just one point load. Okay? And when we talk about, I'm going to write this out since we're vodcasting, simply, hang on. Simply supported beam point load, or maybe point loads, depending on where we end up with time. What we're talking about here is just a beam that has a fixed support on one end, a rolling support on the other, and we have some load that might be in the middle or it might be offset. Let's see if I can work an example. Let's look at number 5.2. And we have a point load here. Okay. This is called point A. The place where the point load is applied is B, and the end point is C. The entire length of this beam is just given the variable L, and the distance from here to here is called small a, and the distance from here to here is called small b. All right, so they ask us to draw a shear bending moment diagram. Well, in other words, what I really want to point out here is the solution is graphical. And I'll show you the structure of that solution. And in each of the cases in Chapter 5, we're going to have a graphical solution. Now, what this consists of are 3 lines that are stacked on top of each other that represent the length of the beam. The first is the loading diagram. The next is the shear diagram, and the last one is the moment diagram. Okay? So we already know how to construct a loading diagram, which is we draw the reactions. This is the reaction at A, the reaction at C, and the point load. Right? Now, what are the values? This is kind of complicated by the fact that we don't have numbers, and I'm trying to decide if I want to do numbers or if there's a better, let's just say this. The authors really like to keep this in letters so that we get the principles of what's going on, but let's just add some numbers to this. Let's say that the length of this beam is 48 inches, and the distance A or B is 36 inches, okay? and that the magnitude of P is 100 pounds, right? So, because I want to make this kind of as I want to bring in as much information as you already have so that we can start from not an unknown point where maybe the variables will be the confounding factor, which it shouldn't be. All right. So for loading, the first thing we know that we have to do, we know that we have a 100-pound force pushing down. We have to do statics to find out what the reaction at A and the reaction at B are. We know that they're going to sum up to be 100 pounds. But we have to use moments. We could take moments about A, for example, because we know that the moments about A are going to have to sum to 0. This is summation forces Y equals 0. We also know that the summation of moments about A is 0, so we pretend like we have a pin here, and we say that the force P times the distance A produces a clockwise moment, which is negative, about point A, and that the reaction at C, I think I said, yeah, there you go, C, times the entire length, which is L, equals 0. All right, so this is a very general equation, but since we put numbers in, we can say minus 100 pounds times this distance A. Well, we know that the whole length is 48 inches. We know this is 36, so we know that this has to be 12 inches, right? Very good. 12 inches plus the reaction at C times the length, which is 48 inches, equals 0. We can solve this for R sub C. It's 100 times 12 divided by 48, which is 25 pounds, right? Because this divided by this is 4, so it's 100 over 4, which is 25. All right, so my reaction at C is 25 pounds. And looking at my beam, that means this has to be 75 pounds, doesn't it? Don't have any choice otherwise. All right, I have constructed my loading diagram. Now I need to construct my shear diagram, which means what is the shear everywhere in this beam? And the way that I do it is I have to do cutaways every time there is a change in the loading condition, I guess is the best way I can say it. So that means from here to here, if I cut from here to here, somewhere along the distance of A, I would have 75 pounds pushing up. And that tells me that everywhere I'm going to have a V force equal to 75 pushing down. Or to do the statics, I would say 75 minus V equals 0, or 75 equals V. So this is positive, and if you remember when we talked about sign convention, I said that down cut on the left is or cut on the right is positive, so that fits. So that means between here and here, my V diagram looks like this. Everywhere from here to here, it's 75 pounds pushing up. Well, what happens if I cut it here between the load and B? Well, if I continue to cut it this way, I have 75 pounds pushing up, I have 100 pounds pushing down, and if I do a cutaway here, and I call it like this, I just call it negative, or I call it downward, which in this equation as an external load would be 75 minus 100 minus V equals 0, negative 25 minus V equals 0, or negative 25 equals V. What it means is that right here we have a discontinuity where it flips to minus 25 pounds. So this is what my shear diagram looks like for the beam. Now there's a couple of interesting points here. One is shear tends to have discontinuities like this, which is why it's a big deal. I mean, you go from having a shear of positive 75 to 25 in the opposite direction. And that's why, and you can see that would happen at a point load, wouldn't it? You'd expect this, that if the beam were going to shear off, that's where it would shear off, where you're going to load it. So shear tends to concentrate in these ways, and they have these discontinuities. So shear diagrams are often jaggedy looking, okay? Moment diagrams, not usually, but shear diagrams will look jaggedy like this. Now, there's one other thing I wanted to show you in terms of the sign convention. If I had cut the other way, if I had started here, here's my beam, and I have 25 pushing up, and now on this side I would call this up, right, according to my sign convention. When I do that, I would have V plus 25 equals 0, or V equals negative 25. That's exactly what I got cutting it this way, isn't it? Okay, so it will work either way. I tend to work from the left to the right. If I'm doing this on my own, I would just do it however I felt like it, but I try to be consistent in class. And if you wish to cut from one side or the other, there's no barrier to you doing so. But while you're learning the process, sometimes it's easier to just pick a direction and run with it. So cutting from the left to the right just allows you to eliminate a lot of sign conventions. So, and that's where the problems always end up with shear moment diagrams. All right, now let's go on. We've got two parts of three of our graphical solution. We have our loading diagram, we have our shear diagram. What about the moment diagram? Well, when we talk about the moment diagram, we have to go back to our load diagram to do our cutaways. So we have 75 pounds, and then at some distance we have 100 pounds, and then at some other distance we have 25 pounds. All right, so every time that there's a discontinuity, once again, we want to cut. So if I cut between here and here, if I think about my moment at the beginning, my moment at point A, it's going to be equal to 75 pounds times the distance, which is 0 or 0. So that means that my moment is going to start out here at a value of 0. But what happens when I come out here to 12 inches? Well, the moment at 12 inches, if I cut right here where this distance is 12 inches, what I have is, I'm trying to think about how to describe this. All right. I always draw a positive moment, first of all. And this is my moment. That's the response. So from 0 to 12 inches, the moment everywhere along here is going to be 75 pounds times the distance. So let's just say at the end it's going to be 12. This moment that's produced by this force times this distance is going to be negative. The moment I've drawn, the responsive moment, is positive because smiley face is positive. Those two things equal 0. When I solve for this moment, this comes over the other side as a positive. 75 times 12, which is 750 plus 150, that's 900 inch pounds. All right, so and if you think about it, this is a linear relationship, isn't it? Halfway in between, the moment's going to be, when I'm right in the middle at 6 inches, this is going to be 450 pounds. So it's going to go from a value of 0 to a value of 900 inch pounds in a linear fashion. So my moment diagram looks like this. Okay. Well, what happens from here to here? If I continue cutting in the same manner that I've cut, I have 75, and I have 100, and this distance is 12, and this distance is 36. Okay, so I'm going to start cutting right here, and there's two, and then I'm going to put that positive moment just the same direction to keep my sign straight. All right. Now, I don't want to start to the left of the 100-pound force. I want to start just a smidgen to the right of the 100-pound force. So here at 12 inches, just right after this, if I think about cutting right here, this 75-pound force is going to be multiplied by 12 plus a little bit. And that's going to be negative because the rotation is clockwise. The 100-pound force is going to be a counterclockwise rotation, so it's positive. So right at the beginning, it's 0 plus m equals 0. So right here, I still have the same value. I have 900. But what happens when I come an inch out into this? Well, I have 75 times 12 plus 1, which is 13. 100 times 1 inch, or excuse me, yeah, because the 1, I just have a 1. If I'm cutting right here, my moment arm is just 1 for the 100, plus m equals 0. And I can go on clear to the end of this, where I have minus 75 times the entire length of the beam, which is 48 inches, plus 100 times this distance, which is 36, plus m equals 0. And if you do the math on this, you'll find out that these have the same magnitude. They're both 3,600, so you get m equals 0 at the end of the beam. Well, if you did this a whole bunch of different increments, what you'll see is it's linear once again. Starts at a maximum of 900, comes down to a minimum of 0 in a linear fashion. And so this is my moment diagram. Okay, and I'm going to do one right in the middle. I'm going to do one right here, like where this is 18 inches, just so you can see the value. Right? So if I were right in the middle, I would have 75 times 12 plus 18, producing a negative moment, plus 100 times the moment arm of 18 equals 0. So I have minus 75 times 30, plus 100, oh, sorry, plus m. 100 times 18 plus m equals 0. So m, I'm going to bring everything over the other side. 75 times 30 is 750 times 3, which is 2250. Yeah, 2250. This comes over 2250 minus 1800. Got my signs correct? So right in the middle, the value is 450. So does that go along with this linear distribution? It sure does, doesn't it? So it's 900 here, halfway in the middle, the value is 450, still in inch-pounds, and here it's 0. So this is the solution to the problem. So in other words, it's not x equals this, or it's not an equation. It's 3 graphs stacked one on top of each other, each of the same length, each representing the length of the beam, showing the loads, the shear, and the moment responses. All right, so do you have any questions? This takes a while to get used to. I swear it is not difficult, but it just takes a little bit of time to get used to. So I would like you to attempt to do, for your homework, problem 5.2, which is the one I've just used using numbers, only I would like you to just keep this in letters, do the literal equation instead. And I'm looking to see if we have any more point load problems. Ooh. Let's do 518, shear moment diagrams only. They do a little bit with the cross section on that, and we'll talk about that later. But for tonight, do 5.2 and 5.18, but for 5.18, just do the shear moment diagrams. All right. So that's it. I'm going to stop streaming, and we're done for the day.